Hey everybody, my name is Adam Pingle. I spoke here a couple of years ago. I think it was hosted elsewhere over in Oakland. At that time I was about to join Ravelaw as VP of Engineering. That company has since been acquired by LexisNexis. That was back in June of this year. I've been the VP of Engineering at Ravelaw. I'm currently Senior Director at LexisNexis. My team span data science, which includes computational linguistics and machine learning, all the way up through and including the client-side apps, the products that we build and put in the hands of our customers. I'm going to be speaking less to my work experiences and a little bit more about kind of opinions and experiences from academia over the last quarter century and how I see that relating to the work that I do. My background is in computer science. I've got an undergrad degree in computer science and was in a PhD program in computer science with a major field in programming languages and minor fields in AI and linguistics. I left that a little bit early, came back up to the Bay Area with a master's degree. And I've mainly been in management over the last 5 years. So I'm going to be talking about a lot of things, including category theory, for instance, that I'm, in most respects not qualified to be speaking about. But we bump into it a lot here in functional programming and Scala, and I think talking about where that's headed is important for this community. And so I'm going to describe how I view the state of the ecosystem here in Scala and talk about a few concrete things that I think we should be doing. Well, a few things we should be doing, one of which is fairly concrete and I think very defensible. The second one is a little bit more vague and less clear. And the third one, I'm going to stick my neck way out. It's a very speculative assertion. And I should say also, I was originally intending to talk about, this is a picture of the axellang.org. It's an open source project I've had running for the last 6 years or so. I've recently been adding more visualization capabilities to it. But I decided that I wanted to focus on this question that Rob Norris asked last year. I think it was halfway through the last panel. The panel was, what's the future of functional programming? And he asked this great question, basically said, we keep coming to these conferences year after year, and I think he used the word craze. 5 years ago, we're talking about monads. 2-3 years ago, it's free monads. Last year, fixed point types. Where is this going? Where is it going to settle down? I think that the point's also being, it's not easy to keep up with this stuff. My day job is management. I've only got so many hours a week to keep up with the latest theories, and it's a lot to handle. And I think there's also an argument that some of these abstractions get more powerful, but more abstract and a little bit harder to learn. So where is this going to settle down? And on the panel last year, there was a great 10-minute response to that question. And I think some of those themes are going to come up in my response as well. But another point I would make about the question is it's really, really big, and I think this is the kind of question where focusing on a specific community or a specific use case is really important. So the use case that I'm interested in talking about and thinking about is data science, machine learning, artificial intelligence, natural language processing. I also need to be building distributed systems. I want to get concurrency right. I want to handle errors correctly. But I think there's this other set of concerns which have to do with building machine learning libraries that I want to focus on today. So this is kind of, I encoded my mental image of how I think about the Scala ecosystem. And these are both fairly subjective axes. So on the x-axis here, I've got kind of the degree of lawfulness of a library, and the vertical axis is the interest level that data scientists that I've known in my experience would have for those libraries. So it is not hard at all to sell scikit-learn to a data scientist. That's 100% score. They love that. On the other hand, something like CATS or Scala-Z, I've had discussions with data scientists about those libraries, and it's hard to motivate. It's hard to get them really excited about it because it doesn't help them do their job, certainly on the short term. And also, I would add that a lot of the people that I've worked with in those roles don't really have, they might have a statistics background, but they don't really have a math background. They don't have abstract algebra. Actually, I don't know that I've worked with a single person who does. Maybe one guy on my team currently. And so what I think ends up happening then is that we end up kind of neglecting this upper right portion of the ecosystem. Now I do have some non-Scala projects listed here, so I've got some Java stuff, Hadoop, Guava, Juice, Mahout over there on the left side. There's a couple of Python projects up there. There's one Haskell project called HLearn that I put in the upper right there. That's something that Paul Snively mentioned last year that I've spent a little bit of time looking at. But I think coming to these Scala conferences, we end up talking a lot about this stuff. Scala's Ed versus Cats, and Matryoshka has an amazing library. And we've got to get this stuff right. But at the same time, I think, somebody, I, for one, am kind of interested in using some of these techniques to implement some of the algorithms that we see on kind of the upper left of this plot. And there's a lot of the stuff occupying the upper right quadrants here are written by current Spire employees, former Twitter employees, things like Algebird, Brushfire, Scalding, Frameless. Spire, if you haven't used it, is this incredible library that I think was released around 2013. It's got a lot of type classes from abstract algebra. So if we think of the Haskell type classopedia that has monad and applicative functor and that sort of thing, there's another set of type classes which complements that really nicely from abstract algebra. So those are things like vector space, metric space, group, and that sort of thing. So why would we want to do this, to be building libraries in the upper right-hand corner of that plot? I think there are three categories of reasons. One is for all the same reasons that any other software you would build could benefit. And I'll give a couple of specific examples of that. The other is to help us communicate with and leverage other fields. And then kind of the most speculative one that I'll stick my neck out and say I think we're not done building AI algorithms yet, and we need concepts that are going to help power those things. And I think the mathematics that we're finding to build lawful libraries could potentially be fodder for new generations of algorithms. So the usual suspects why we use FP apply to machine learning systems just as they do anywhere else. We're building distributed systems. At work, we tend to build a lot of supervised models. So we're creating in-house annotation data sets. We're training and evaluating those models, and we're deploying them quickly into the product. So there's some new workflows there, but for the most part, it's just software. And so referential transparency is as important to those kinds of systems as they are anywhere else. And also, I think the easy parallelization story it works well. We're able to get data scientists which don't necessarily have training in distributed systems to build algorithms that scale out kind of naturally from day one. But the one specific example I might bring up about controlling side effects that I've seen apply to machine learning is tracking entropy consumption as a side effect. I've been kind of waiting my whole life to run into that as a bug, and I finally did a few months ago. So consuming entropy, whether you think about it as I/O or not, it's definitely a side effect. And at work, we process our corpus every week anew. We build a knowledge graph from the legal case law every week. And so because we're doing this, we need to monitor very closely how it's changing week over week to make sure we haven't introduced any bugs. So over the many months, year to two, we've been finding those bugs and eliminating them. But there was one lingering little issue that led to a little bit of noise week over week. And it took us several weeks to track this thing down, but it turned out, I think it was some kind of deep learning model. It was an H2O library that it turned out consumed a little bit of entropy when you applied the model. And had that shown up in the method signature, we would have probably found and eliminated that bug a lot more quickly. So I think that's one little maybe machine learning specific side effect I think is worth noting. So to talk about HLearn a little bit, That was that point that was kind of in the farthest upper right point of that chart of the ecosystem. Of course, it's a Haskell project. It does make use of patterns from abstract algebra. And I've stolen this chart from its README file, and it's got a lot of kind of benefits listed in that second column. And these are things that I can sell to data scientists and get them excited about. So things like parallel batch training, online training, cross-validation, weighted data points or fractionally weighted data points. Those are of interest to data scientists. And the way that this particular library happens to achieve them is by leveraging patterns from abstract algebra. So those are listed in the first column: monoid, abelian group, R modules, vector spaces, functors, and monads. So I think that's great, and it shows an example of what we can do if we bring together these two things. However, I would say those are not necessarily my pain points. So the speed of cross-validation was never necessarily a bottleneck. But I think there's this other point that's made in the documentation. It currently has the fastest nearest neighbor implementation for arbitrary metric spaces. That's pretty interesting, to be able to kind of parameterize this algorithm in terms of arbitrary metric spaces is not something I've seen in a lot of machine learning libraries. So in the fact that it's fast, at least to other things that do that, is great. So that the author spent a lot of time in performance optimization. I think the challenge here, though, is to find an example of a sort of non-standard, non-Euclidean metric space that's going to be really motivating, that's going to allow that data scientist to solve a problem that they've not been able to solve previously. So that's sort of the concrete stuff. There was a second set of issues around just being able to leverage what's going on in other communities and within our own community here of Scala. And I think of the Tower of Babel, the tale of this king building a tower and making God angry, and so he destroys the tower, and he creates the confusion of the tongues, creates all the languages on Earth. And I think sometimes I feel like that, both in the Scala community or just as a scientist learning about other fields, is that we are speaking, we're basically mutually unintelligible to one another. And I had a specific example. I'll try to get through this anecdote quickly, but I had a specific example of this in grad school. I was taking a course on causality from Professor Pearl, and he was talking about the Simpson's paradox, which comes up to statistics. It's basically, I think the canonical example is looking for gender. It's either hiring or it's gender bias in hiring or application admissions. And it doesn't show up when you look at UC Berkeley as a whole, but when you look at each department separately, it's clear as day. So that's Simpson's paradox, and the way it was being described reminded me of the prisoner's dilemma, an iterated prisoner's dilemma. Something about the way collusion works with the iterated prisoner's dilemma reminded me of this kind of nonlinearity that you see in Simpson's paradox. And so I raised my hand, made that point, and basically got blank stares from everybody in the classroom. Now I think that's probably share the blame, spread the blame around to a lot of parties there, but I didn't have the language to be able to communicate what I was saying very effectively. And I think the writing style of the book that we were using wasn't something that worked well for me. And then I asked the TA about it on the way out of class, and he didn't understand what I was trying to say either, but it kept gnawing at me. And it was either a few months or a year later, I did some Googling, and sure enough, this was a thing. And in fact, Nimrod Megiddo, who had done a lot of game theory research, I think he's local to the Bay Area, he had written Perl making exactly this point, and this letter was posted up online. So, I'm not the only one that's having trouble getting my point across between these fields. And these are smart people. Perl is brilliant, Megiddo is brilliant, but there's lots of debates, and I think some of that energy we could focus a lot better just as a community. So I think, I think sometimes of programming and programming communities as trying to compress our symbols and our ideas. We're looking for ideas that allow us to express programs more succinctly, more correctly, and of course, the symbols that we're choosing have to also apply to enough situations and that they're worth it. But I think that's a lot of what mathematics is doing. Another field that I've had some exposure to is linguistics. I see a lot of kind of, we're basically trying to identify short, elegant models that explain the phenomenon we're studying. I think science in general is doing this to some extent. So one of the things that I found immediately upon leaving grad school, coming back up to San Francisco in 2009, was there was this burgeoning Scala community, and kind of adjacent to that, category theory meetups. Vlad, I don't know if he's in the room right now, I saw him here today. He was running a lot of these things. And one of the first papers that came across my desk was this paper known as the Rosetta paper. It's called Physics, Topology, Logic, and Computation, a Rosetta Stone. And again, so we're getting to the point in the talk where I'm not really qualified to be speaking about this stuff, but it's at least inspiring to know that someone out there has in hand a theory that they can use to very deeply describe the shared dynamics and shared structures across these four different fields. So the last two columns, logic and computation, we know that as the Curry-Howard isomorphism, this deep correspondence between functional programming and logic. But using the category theory concept described on the leftmost column, we can also make deep analogies to physics and topology. I think I'm going to skip over a couple of anecdotes. So the last most speculative point I'd like to make is that I think a lot of machine learning and AI algorithms are using pretty old algebraic structures. Tensors, for instance, were formalized in the 1890s, and they're the latest craze. I don't think, category theory may happen to be used in the implementation of some algorithms, but I don't think it's really central to the understanding or the theory of any machine learning algorithm that I'm aware of. And I think that there's potentially a lot of really interesting work ahead. So I've got Dave here from 2001 on the picture just to represent that. I think this can be kind of mind-blowing, especially that I don't have kind of the mastery of category theory that I would need to be able to do this stuff. But I read about it, I bump into it often enough that I think there's something there. And so I think about, what can I do to help, if 20 years from now that's going to pan out, what can I do to help myself get there, and what can we do as a community to get us in a position where we're going to be able to grok that stuff? And I think we need to start occupying this upper right-hand space. An easy way to think of project ideas is to just sort of pick 2 points here and then just kind of draw a line to the right, draw a line up, and for instance, Spire is a great one. Implement some libraries implement some algorithms from Pyro, which is a new probabilistic programming library from Uber. Implement some of those algorithms using some of the abstract algebra type classes from Spire. I think it's pretty easy to generate these things, and I think then as a community we'll be better positioned to take advantage of what I think will be a new generation of algorithms. And I'm getting a little short on time, but one thing I'll mention is I think there's some evidence of this with a genetic programming project called Polytope. This I saw tweeted about several months ago. Someone's using Shapeless to implement some of the aspects of genetic programming, which, if you haven't run into that, it's basically an evolutionary search algorithm where we can think it's basically mimicking sexual reproduction. The programs are floating around in an arena. There's mate selection based on a fitness function, and then instead of DNA splicing, we're basically taking Lisp expressions and kind of swapping sub-expressions to create a new program. Well, if you don't do that correctly, or if you don't pay attention to the types, that can easily result in in an expression that's not well formed, that doesn't type check. And so I think this Polytope project is using some techniques from Shapeless to address that. And I think I'm going to leave it at that. So yeah, happy to take any questions.
Thanks, Adam. That's great.
Yeah.
Questions?